Today we are going to hear from Dr. Aleksey Baldygin, and he is the technical consultant for Cruise up in Canada, the entire country of Canada, and is going to be presenting a very nice presentation today about the differences between Dyne pens and contact angle work. So I will shut up and let Aleksey do his thing. So good luck, Aleksey.
Thank you, Leland, and welcome everybody. Good morning, good afternoon, it depends on when you are. And so today I will give a talk about the Dyne pens, and I will try to give you the alternative point of view. So before we move into the Dyne pens, I will try to give you some motivation of why people are doing such measurements and why would people switch from the Dyne pens if they feel uncomfortable using them. So when I talk to my customers, I often see them using the Dyne pens, and it is often for me to hear that they need to be at the energy level of 38 dynes or higher. And so this will be the first question to me if you are one of those customers. So I'm going to run the first poll where I want to ask you if you heard or was told that my energy level or Dyne level should be greater than 38 or 36, 38 for good adhesion, printing, laminating, etc. Depends on what you're doing. The main thing here is the numbers, which are given by the suppliers of adhesives, paints, coatings. So I'll just give it another second so you can all answer. Okay, we got the answers in. Let's share the results. So as we can see, we have 32% in the audience who actually heard or were told about this in the past or even in the present. Then we also have a significant group of people who never heard or they don't know what I'm talking about. So let's dive in and understand what it is. So on the screen as of right now, you see the image of the surface, and on the left side you have drops. In the middle there is a nice film, and on the right you have some transitional wetting behavior. So this is essentially the test ink or the Dyne pen which was used on the surface, and the experienced user will tell you that if you have a nice wetting, then this is the right level. So let's say I use the boil, which has a nominal number of 40 millimeters per meter, and I have a very nice film on the surface, and this is my middle case. So from this point, I can comfortably say that my Dyne level is, or energy level is 40 millimeters per meter. The problem is customers also tell us that it is very user subjective. So some customers see that it's 40, but others may think it's 38 based on their personal experience and their personal preference. On top of it, you can't really store the values, or you can't go back in the history, let's say, check the data from 6 months in the past or 9 months in the past and understand what was measured and how it was measured and who measured it. So here's an example. So I have two parts. So in this case, I have a stainless steel part. So the one on the left side is untreated part. So this is essentially the raw material. It's a stainless steel surface. And then on the right side, I have the plasma treated stainless steel surface. Then we're going to measure the energy levels using the testings. And what we can find is that the part on the left has a 38 dynes and the part on the right has a 64 dynes. Well, the problem is typically people say the higher the energy level, the better the adhesion is, right? But in this specific example, what is happening is the part on the left experiences the good adhesion while the part on the right has the bad adhesion. So this tells me that something is going on and we need to dig a little bit deeper. So first we'll start with a little bit of theory. So it was already mentioned by, I believe, Daniel, the rule of Dupree. And essentially what this rule tells you is if the energy level of your solid substrate is greater than the surface tension of your liquid, or let's say coating, ink, whatever you apply on the surface, then you're going to have the perfect wetting, or it will form the 0-degree conic angle. Well, the problem is the Dupree, he didn't differentiate between the polar and non-polar liquids, and basically this rule tells me that it works for any type of liquids or any kind of liquids. It also tells you that if you have two liquids side by side placed on the same surface, then the liquid with the highest surface tension is going to have a larger conic angle than the liquid with the lower surface tension. To simplify it for you a little bit, I made this a nice sketch where I have the same surface with 55 dynes, and then I have the liquid in the bottle on the left with 15 millimeter per meter surface tension, and I have the liquid on the right with 60. And as you can see, the liquid on the left forms the film, and the liquid on the right forms a drop. This is all done based on the rule of Dupree. So here's an example. I have a substrate. So on the left side and on the right side, I have exactly the same substrate. So this is identical substrate, but I have two different liquids. So my question to you is, where do I have the liquid with the higher surface tension? And that's what my second poll is about. So once again, so which liquid from these two has the highest surface tension? Is it the one on the left, or is it the one on the right? So 10 more seconds for you to answer, because I can still see the answers are coming in. Okay. So as you can see, based on the poll, we have 84% of people saying that the liquid on the left side has the higher surface tension, and the absolute rate based on the rule of Dupree, if they follow it, right? At the same time, we have 16% of people saying that it's on the right side. So let's see. So in this case, what I have the glass sample. So this is a glass substrate, and you can do this experiment in the lab if you have the goniometer, or even if you don't have the goniometer. The only thing you need is the glass substrate and two test liquids, water and diamethane. And surprise, surprise, on the left side I have the diamethane, while on the right side I have water. So now if you look into the literature and if we check the surface tension of these two liquids, what we'll find is the surface tension for the diamethane is 50.8, and then the surface tension for water is 72.8. So unfortunately, 84% of our audience were wrong, and 16% were right. So the liquid with the highest surface tension is on the right side. But I guess at this point, you're going to ask me, why is it happening, right? And what is the phenomena behind it? So once again, the rule of Dupree doesn't take into account the polar and dispersive parts. But when the wetting process is happening, we have to take them into account, and we have to make sure we have agreement between the polar and dispersive parts. So a little bit of recap. So this is something which was introduced to you by Thomas and Raymond and Daniel in the past. So when we're talking about the surface tension for the liquid and surface free energy for the solid, we have the overall number. So let's say for the water is 72, and then it could be a sum of dispersed and the polar part. And there are obviously some non-polar liquids, and there are some non-polar solid substrates. So down below, I provided you some examples. For example, N-hexane has overall surface tension of 18.4, and the polar part is 0, or like water has 72, and the polar part is 51. At the same time, on the right side, I have examples for some plastics. For example, polyethylene, high density, has the surface tension of 35, surface energy of 35.1, and it is non-polar as long as it's not treated. This is also a bit of recap from the lecture on Friday from Daniel. So when we are talking about adhesion, or we want to understand the adhesion between the solid sample and the liquid, we need to break down the solid sample and the liquid into two parts. Well, as long as the polar part is there. If the polar part is not present, then we'll just have a single part which will be equal to the overall energy level. And example on the left side is I have the solid with overall energy level of 50, polar part is 10, and then I place it in contact with liquid A, which has a surface tension of 50 and the polar part is 10. As you can see, I have a perfect wetting, I have a 0-degree contact angle, I have 0 interfacial tension, and I have a significant work of adhesion. At the same time, if I switch from liquid A to liquid B, where I have the opposite case, so polar part is 40 and dispersed part is 10, then the contact angle will go up from 0 to 53 degrees, and the interfacial tension will also cross the limit, which was defined by Dyne. At the same time, at the bottom, what I have 3 examples. So I have the sample, which was measured with the goniometer. So I got the energy level of 67.9 using 2 liquids, and the polar part was 42.3. While the testings, they simply failed. So they were not even able to see this such energy level. And this is something else I see quite often is when we start doing the measurements with goniometer, customers tend to tell me, hey, I have never seen such a high energy level. Like your machine is probably measuring something wrong, right? No, it's not measuring anything wrong. It simply takes into account the polar and dispersive parts. Back to my example. So I have 2 liquids. I have diamethane and water. So their properties are in red. Their properties are in blue. And then the red is the property of the solid sample. So this is essentially glass. And then using the adhesion tool, I can easily calculate the contact angle and work of adhesion and interfacial tension. So I even don't need to do the experiments, for example, for a given liquid, as long as I have those parameters. So going back to practical part. So this is my example of those two stainless steel parts, right? So I have a stainless steel treated, and I have a stainless steel plasma treated, and then the last component which is needed for me to complete calculation will be the glue. When I place 2 together, stainless steel untreated and the glue, I can calculate the interfacial tension between the part and the glue, as well as work of adhesion and the contact angle. I can do the same thing for the plasma treated part. And as you can see, the glue shows us 0-degree contact angle, and honestly there's no surprise to me, because in most cases you'll find that the glues paints, they will be non-polar because they're designed to the regular consumer who is not able to modify the surface and has to deal with a highly dispersive surface. Work of adhesion, in case of the plasma treated, indeed it's higher than in case of the untreated part, but what's important is the plasma treated part experiences high interfacial tension. So this is essentially why the part is failing, and that's why we're seeing some delamination for our glue. So if you look through the table, so both of them are perfectly wetted again, so they show comparable adhesion, and they not define that work of adhesion has to be greater than 65. So in both cases we have greater than 65. And then the interfacial tension was defined to be less than 6.5. So in this case, only the treated part matches. So let's again have a closer look at our parts. So at the bottom, 38 is the numbers which were measured with the testings or Dyne pens. And then at the top, we have the energy levels obtained from the contact angle measurements using the water and diamethane. Then we have this very nice area where the glue wets perfectly the surface, so the contact angle is 0. Then we also have the surface where the adhesion process is happening, and this can clearly be seen on the left side, and this is due to the interfacial tension of 1.7. At the same time, on the right side, we see the delamination. So this patch, that's where the glue failed, and this all happened due to the 21.3 interfacial tension. So again, in this case, there was no need to plasma treat. So basically you wasted your time and money on doing such such thing. Instead, you should have just checked and optimized your surface. So a little bit of the summary. So overall energy level is more or less uninteresting, or even it's useless in this kind of applications. So greater than 38 does not necessarily lead you to the good adhesion. Even when people tell you that you have to be greater than 36, 38, it's false. So instead, what you should do the quality control or the quality check for both the polar and dispersive parts. And if both of them are in the range, then you're good to go. And only if you have the information about the both parts or polar and dispersive parts, then you can only predict the wetting and adhesion. If you only have overall energy levels, it's pretty much useless, because there is no way for you to see what is happening between your adhesive and the solid substrate. So this is my example number one. The second application, and I believe we had a couple of questions over the past 2 weeks, is about the cleaning and how we can make sure that my surface is clean. Can I do the measurements for the energy levels, or what should I be doing? So this is application number 2. So my experimental setup is pretty simple. So I have the contaminated steel plates. Then I have the ultrasonic cleaning pass with a 3% mucosol solution. And then I can change the dwell time, so how long I'm going to clean it. And then I can do the quick check using the mobile unit, mobile surface analyzer. Going back to the equations introduced by Thomas. So this is the Young equation, where we have the energy level of our solid substrate is a sigma S. Then we have the sigma L is the surface tension for the liquid. And then we have sigma LS. This is the interfacial tension between the liquid and the solid substrate. What else we can do? If I have the insoluble contamination on the surface, let's say it's an oil film, and then I place the water drop on the surface. So the water drop is not going to react with the oil film, but instead it will just stay there, and it will form the drop with a pretty high contact angle. But at the same time, if I have some soluble contamination, for example, it could be some surfactants left behind on the surface after the cleaning process. So those ones can migrate into the liquid. And then what we'll see how the contact angle for my test liquid changes over the time. This one is just a quick video, shows that you can do the measurement in 2 seconds. But once again, if you're interested in understanding how this is working, feel free to go to the www.cruise.academy and check the video, which was posted on Friday. It's a nice 40 minutes demo video. Now, in terms of data which you can get from Advance, after completing the measurement using the 2 test liquids, water and diamethane. So you can obviously have the overall energy level. So in this case is 36.6, but then I can also have a breakdown into the polar and dispersive parts. Using the dynamic function, or basically measuring the contact angle over the time, that's what Thomas asked you to do. It helps me to understand if there is a contamination on the surface, and it helps me to understand if my test liquids are reactive with the surface. And at the end of the day, once I have the overall energy levels and the polar and dispersive parts, I can predict adhesion. Going back to example. So I have 5 stainless steel parts. I have different cleaning time. And then what I'm going to do, I'm going to measure the energy level, overall surface free energy for each sample. And I'll see that I'll try to understand the breakdown of the polar and dispersive parts. So this is my table. On the horizontal axis, I have the cleaning time, and the vertical axis is my surface free energy. So when I just started, when I had the original part, so before cleaning process begins, the contact angle for water was in the range of 93, 92, and for the diamethane, it was a 51. As you can see, there is a difference between the left and the right contact angles for the water. So this is already clear indication that there is something wrong with the surface. So if you're seeing the contact angles being different, like by 5 degrees or sometimes 10 degrees, this is clearly that you have some sort of contamination on the surface. And this can be easily checked if you remove the instrument or if you just look at the drop on the top, you will see that the profile of the drop doesn't look as a regular profile. Then I can perform the same measurement after the 900 seconds. So that's what I did. And as you can see, the contact angle for water went down. So now I'm down from 93, 92 to 7.2. So that's a significant decrease. As well as for the dimetane, I'm down from 51.52 to 27.9. Another thing is I want to point out, because it may not be visible when I have those images, is in fact, you don't really have to clean for 900 seconds. You can stop your process at around 300 seconds or at around 120 seconds, because past this point, you're not doing much to your surface, so it's already at a constant level. And this is another good practical example, is when people are doing the cleaning with IPA wipes. I don't know how many of you are doing this out in the field, but this is pretty common, is when the surface is cleaned with IPA wipes, and the question will be, how long should I clean? Again, simple measurement can help you to answer this question. You clean, let's say for 5 seconds, then 60 seconds, or 360 seconds, and you do the measurement thereafter, and then you can clearly see the difference. You can also set up the program in the way that it will work as a quality control tool, but in this case, you have to have your standards. So let's say for the cleaning process, so once it's established, once you know your levels, you can tell the software that please tell me when my polar part is greater than this, so that I can stop the cleaning process. So advantages of the method, obviously, this is simple. It's just one-click execution. It's extremely fast, so you don't spend much time, and it is user-independent. So this is if you compare to the testings again and the Dyne fence, right? Plus it's local, so everything is, we have this information about the given part of the sample, and we don't need to get the sample, so we can just use the entire sample. So now I think I still have some time. So I will give you another example, or I will try to answer another question, is why the testings cannot tell the whole truth about the surface energy. So before we would just say, hey, they give us the wrong data, but why is it happening, right? And in this case, we performed the study. So this was a feasibility study done in our lab in Germany, in Hamburg. Where we compared the results from the goniometer to the set of the testings. In order to cover all possible industries and cover pretty much every single company, is we set up different samples. So in the overall, we had 14 different samples, from glass to wafer to aluminum foil to some plastics to the PDMS, to some cloth. And in terms of testing system, so we use the goniometer, we use the benchtop system, the DSA 100, with 3 test liquids in this case. So it was water, dimetane, and ethylene glycol. Then we use the formamide, and we use the ethanol-based testing. So that's just for your information, the formamide will be the blue in color, and the ethanol-based will be the yellow color. So first we started with the polypropylene, and this is common type of plastic, I would say nowadays. And while after completing the measurement, we could clearly see the energy level to be 29.6. Then we performed the same using the ethanol based testing. And if we have experts in the audience, then they can clearly tell me that this is probably 30 or less. And then we use the blue one, and this is definitely dead solid on 30. So obviously at this point you can tell me, hey, Aleksey, this is sounds good to me because it gives me the right data. But let's have a closer look and try to do the same thing on other samples. So we did this, and in this specific table, what you'll find is the red or colored in red is the faulty measurements. So it's where the testings or we're basically saying it's significantly greater than, there is a significant difference in numbers from the contact angle measurements. The green color is where we have the more or less perfect match. And then the gray is where the measurements couldn't be completed by the testing simply because it was outside of their measurement range. And the question you might ask, okay, why is it happening? So if you carefully look at your solid samples, and if you look at the polar and dispersive parts, for example, polypropylene untreated will have the 0 polar part, same as a Teflon or same as polyethylene, then it's working. But the moment we have the polar parts, so the moment we have the polar groups, then this is no longer working, and we are no longer able to get the right numbers. And the tricky part is it's coming from the way how the testing, so Dyne pens are manufactured. So when they manufacture them, the companies, they do provide us nominal numbers. So if you have this test kit in your lab or on the production floor, then you can clearly see the nominal numbers such as 30, 34, 38, or all the way up to 56, or even 72. There are some kits up to 72. But the thing is, they don't tell you on the portal, or they don't tell you what is the polar part or the dispersive part inside each testing. But this is important because, as we know from my first example, is the polar groups interact with the polar groups on the solid substrate, and the dispersive with the dispersive. And if you don't control it, if you don't know this, then you're going to get the misleading data. The last example we did is we set up the system with the automatic stage where we place the sample, and we moved it and it placed it underneath of the plasma brush. Then we applied the plasma, and we moved back into the optical system, or it's basically back into the goniometer, so that we can perform the measurement. So when we did this measurement, for example, we did it at 3 different timestamps. So 0 seconds, and when it's a raw material, so it's untreated. Then we also did after 40 seconds of treatment, and we did after 60 seconds of treatment. So as you can see, after 0 or untreated sample testings, they simply cannot measure because it's outside the range. But what's interesting is even after 40 seconds or after 60 seconds, the testings, they still fail to measure. So they still fail to detect the increase in the surface free energy, especially the blue one. So what it can happen to you is, imagine you're not seeing the increase in energy levels, but you continue doing the plasma treated process. And so eventually what will happen, you're going to over treat your part and you're going to damage your part. The same applies to another sample, again, raw PVC in this case. We did raw sample, and we did 40 seconds of treatment and 60-second treatment. Unfortunately, we had exactly the same story where we were not able to see any correlation whatsoever between the contact angle measurements and the yellow or blue testings. So with this, I'm going to conclude my my lecture, sorry. And I'll just ask you a simple question. So what do you choose, truths or Dynes? I'm not going to run the poll, so you can just answer it to yourself during your free time or when you're going to watch this lecture again. Thank you, and have a great day, afternoon. And with this, I'm going to open the floor to questions.
Great, thank you very much, Dr. Baldygin. First question that I have for you is it true that, and this is something that I myself have heard, is it true that during plasma or flaming processes that only the polar part changes?
No. So so from the practical point of view, it is not true. So I have seen samples where sometimes the overall energy level remains constant. So let's say you're stuck at 50, but what happens is inside the polar group goes down and the dispersive part goes up. At the same time, we've seen parts where the overall energy goes up, and then the polar part, yes, it increases, but at the same time, dispersive part is also going up. And sometimes the dispersive part is overplaying the polar group. So yeah, the answer will be no, this is not true. So you should always look into your sample and you should try it. Obviously, there will be some parts where the pole group only goes up, but there are multiple parts and many samples where this is not true, and you have to do the measurement.
Great, thank you. Next question actually is, can you just give a quick description of what is a dyne, and maybe if you can expand that to are dynes and the millinewton per meter measurement, are those the same? Are they different?
Okay, yeah. It's commonly asked question. So dynes, this is I would say like a slang. It's what people use out in the field when they measure the energy levels, and basically you have one dyne equals to 1 millinewton per meter. So the units which we are commonly use in the gonimeters, it's 1 millinewton per meter, and the units which I often hear out in the field on the production floor will be dynes. So it's a one-to-one. There is no conversion unit whatsoever. It's just one-to-one. So if somebody tells you that I have to be at 40 dynes, means they have to reach the energy level of 40 milliliters per meter.
Great, thank you. The next question I have is, can you, you mentioned that there was some criteria for the allowed range for the, I believe that the question is speaking to the interfacial tension and the work of adhesion limits.
Mm-hmm. Okay, yeah.
Repeat that, please.
Oh, so let me rephrase the question. So the question is, so there is a allowed criterion, or basically the rule of thumb when we have a good adhesion or the bad adhesion. Is it right?
I believe that that's the question. Yes.
Yeah. So if we open the Daniel's presentation, I believe it's Daniel's. There is a table with the reference, and in that table and in that reference, you will see that the work adhesion has to be greater than 65, and this is for the short-term bonding. And then the interfacial tension has to be less than 6.5 millimeter per meter. This is for the long term. Again, if this is your case, or if this is something will be applicable to you, you have to check. So typically what happens is, let's say if you're the automotive company trying to glue bumper to the aluminum frame. So what I would suggest you to do is perform the measurements of your different treatments, as well as understand your adhesive, see what are the numbers you can achieve, and then at the same time you perform the shear test or the break test. And then from those tests, you can find optimal conditions for your case. For example, 6.5 is a good number, but I've seen another company sitting at 8.5. So based on their experience and based on their tests, they found that they have a sufficiently good product when the interfacial tension is 8.5. So there is no point for them to continuing, improving the process, because the part will last a number of years, and that's exactly how long they want this to last.
Okay, thank you. So for surface cleaning confirmation, if you're doing these measurements to confirm your cleaning process, do you need to use two liquids? In our, what we recommend is water and diethylmethane, or is one of those liquids enough?
So obviously I would recommend to use two liquids. And the reason is not because we use two liquids, but the reason is you can have different types of contamination on the surface. So as in my example, imagine you have the oil film on the surface. So if you just use water, what will happen is the water drop will just stay on the surface. It's not going to break through the oil film. It may break through the oil film, but it will take time. So this is something what Prashant showed in his lecture on Monday, is where he demonstrated how the contact angle changes over the time. So imagine if you place the water drop on the oil film and you control the evaporation process. So you control you basically control the volume of the drop. So eventually the water may break through the oil film and will touch the surface, but it may take hours until it reaches the surface. And that's why the second liquid comes handy, because diethylmethane is going to react with the oil and is going to tell you that there is something on the surface. And you can clearly see on such samples, when the water shows pretty high contact angles, it'll be like 90, 100 degrees, and the diethylmethane will start spreading. So the diethylmethane will go from initial of, I'd say 50, 60 degrees, and it will go down to like 20, 30. And you can also see not only the contact angle is going down, but also the base diameter is going up. So these two indicators in the chart can tell you that there is a contamination on the surface. It's not reactive with the water.
Great. Thank you for that answer. The next question that I have speaks to, so the MSA, when it's dosing, the default values at least are 2 microliters per drop. And that the total covered area is relatively small. Your probing area is relatively small.
Mm-hmm.
But can you speak, there's not really a question here, but can you speak to testing, a non-homogeneous surface? And if you're only probing small areas, what information would that give you about a non-homogeneous surface?
Okay, so yes, indeed, when we test with the MSA, so the droplets placed on the surface, they have a diameter about 2 millimeters. But my question will be, is it non-homogeneous on purpose, or is it something you struggle with? So when you perform the measurement, I would obviously recommend to try at least 3 different points on your surface, because I mean, you can be just lucky, right? Let's say if today is your lucky day, you can place it on a spot and you'll get a good numbers. But does it mean that the entire surface is the same? Not really. So for me, it's as an experimentalist, I always do 3 measurements. So I perform 3 measurements in different spots. And then if I see a significant difference between them, so this tells me something about my surface. So this is telling me that my surface is not homogeneous. And then what I can do, I can increase up to 5 sample points. So I can go and proceed with 2 additional points. And if I see all of them be out of spot, out of place, then this tells me that I have to do something about my surface, unless this is something I'm doing on purpose. So if this is purposefully made to be different along a large surface area, then I'm good. But if I'm trying to achieve the consistency along the large surface area, then it tells me that I have to either scrap this part or go back and redo whatever I was doing.
Aleksey, can you speak to the surface mapping capabilities as well with respect to that?
So for the surface mapping, there are a couple options. So for the benchtop system, what you can do is you can essentially set up the large sample, let's say it's 0.5 meter by 0.5 meter, and then you can perform the measurements at different spots. And then the software is going to map the surface and it will show you the high peaks and low peaks, or like valleys on your surface. So essentially, this will be the faster way for you to figure out where you have the problem. And so the interesting thing which I like to do is you take your just regular cell phone. I don't know if you can see my cell phone. So just take a cell phone and then you clean the surface and then you place it on stage and you do the contact angle measurements. And depends how you were holding it when you were cleaning it, you can clearly see direction of cleaning process. So you can see that where you were holding with your hand, the energy level will be relatively low compared to the end point, because at the end point you're applying the larger force. As for the MSA, there is a gantry system, which is basically defines this called LSA product, large surface analyzer, and the same thing can be done up to 3.5 by 3.5 meters, I believe. So yeah, imagine like a large TV screen placed on a platform, and then you do the measurement. And yeah, I hope it answers the question. Leon, are you still there?
Sorry, I was on mute there for a second. So the next question that we have for you is, let me see here. There's a question that revolves around the OWRK theory. So how would a solid surface energy values compare for our method shown of the OWRK model versus, actually, let me separate this out. There's the first part of the question is that the asker is referencing taking measurements with diethyl ethylene glycol, and water. So the first question I'd like you to take is ethylene glycol recommended? And can you speak to any concerns that ethylene glycol may have as a problem?
Oh, is it problem liquid? So I personally don't like ethylene glycol. The main reason why I don't like to use ethylene glycol because it's not stable. So it absorbs the moisture from the environment. So when you're purchasing the nice and fresh bottle from Sigma, Fisher, I don't know who supplier is for you, then it has the surface tension from the table. You use it today, it's all good in terms of pollen dispersal groups for that liquid. Then you store it and then use it 1 month after. And what happens is the surface tension is no longer the same and the polar part is no longer the same. So you can no longer use the literature values. So you can still continue using it. But the thing is, if you're going to use the ethylene glycol, let's say for your test, then you always have to check the overall surface tension and the pollen dispersal parts. Otherwise, you'll be out of luck. And it will result in a misleading data in terms of overall energy levels. At the same time, dimethyl is not pronounced to such changes, not to this extent. And typically your bottle is good for about 2 years until you have to throw it away. Water is, again, quick check. In most cases, we also always have the open source, right? We have the distilled water source in our labs, and we can also maybe buy it from pharmaceutical store if you don't have this source. So those liquids are safe, but ethylene glycol, from my point of view, it's not safe to use. Not from health point, but from the accuracy.
So the other part of that question is, regardless of whatever your test liquids may be, if you were to compare the OWRK model to the WU harmonic mean model, can you give some sort of comparison on which of those is better or advantages and disadvantages?
Okay, yeah, I had this question not long time ago. So really, there is nothing like better. So if you compare OWRK to WU model, they just simply use different equations to calculate the energy level. The data is comparable, but you're not going to get the same numbers right on spot, simply because it's calculated differently. In terms of using 2, 3, 4, 5, 6 liquids, how many you want to use, if you plot them all together, what are you going to see? You're going to see this nice straight line from liquid to liquid to liquid. And the one thing you may see is 1-2% deviation. So this is pretty much useless in most cases to perform more than 2 liquids because you're not going to uncover any additional data. And for the models, again, what I personally find is let's say mainly in academia, there are some groups of researchers. They have a history of using specific model. Let's say WU has been used for 20 years in this specific research group, and they just continue using. And I think they should continue using. They don't need to switch, simply because if they switch the new model, then the data may be offset from what they collected in the past. Inside the software, you can freely switch between, I think, 6-7 models. So there's like OWRK, energy of state, WU, Schultz, serial Schultz, acid-based. So all those models are available to you. So if you want to practice, if you want to explore others, just keep in mind, so some of those will require more than 2 liquids by default. So you won't be able to get the data if you just use 2 liquids. And there is one which will require only single liquid, which is energy of state.
Great. Thank you. The next question here is, so the setup is, we often clean parts with a product that makes them extremely hydrophobic. Okay. So after the cleaning process, the product becomes hydrophobic. Mm-hmm. Would it still be able to measure this using alcohol as your test liquid?
I don't think I understand the question.
I think that the point is the end result of a cleaning process renders the part hydrophobic. And so the recommended test liquids.
Oh, okay. So what they're asking is, so at the end of their process, the surface is hydrophobic, so the contact angles for water will be higher than, like, say, 110, 125. And then they're hoping to use other test liquids to get the surface energy. So yes, as long as those test liquids are not reactive, so they're not changing your structure or whatever you formed on the surface, yes, you can use those test liquids. This is something we also do with Washburn technique. So in the Washburn technique, as you know, the contact angle has to be less than 90 degrees. Because if it's greater than 90 degrees, the liquid is not going to rise. And if the liquid is not going to rise, you won't be able to get the data. So the workaround will be using other test liquids. And so we tend to go through quite a bit of test liquids, could be up to like 20 for a single customer, trying to find out the optimal configuration and trying to find out the liquid which is non-reactive and at the same time gives us less than 90 degrees. So the same thing applies here. Yes, you can use other liquids. The only thing is you may want to try to find the, on both spectrums. So you have one liquid which will be like a non-polar, another one is like predominantly polar. So this way you can get the good data.
Great. So for printing with UV inks, when is Dyne testing useful? And the phrase being used here is Dyne testing. So maybe you can answer that two ways. Dyne testing meaning using Dyne pens or Dyne inks, and then a separate way of, hey, just doing surface energy calculations. So when is it useful when printing with UV inks?
So it could be before you print on the surface. That's what Thomas showed, some data on paper. I mean, it depends where you print, right? So UV inks, what is your substrate? But checking the substrate before, it's good. I've also seen people doing after the printing process. Simply they want to understand what is, okay, let me rephrase it. So it's good to do before printing, and after printing is good too, because you want to know what is your surface, what is your final product. And in some cases, people also do some additional processes after they complete printing. So sometimes laminating, because they want to protect the UV inks. Sometimes they apply some clear coats. So it could be, yeah, so I would say before and after and between. So it's never too bad to have too much data. And the moment you start collecting the data, then you can narrow down and see, let's say this data doesn't show me any results, and this data gives me quite a bit of insight about my product, about the quality of my product.
Yeah. So the last question, unless some last minute ones come in. So we've been showing our handheld instrument as an example device multiple times throughout this presentation. It's called our Mobile Surface Analyzer, or MSA. And the person asking the question asks if that instrument is capable of doing pendant drop surface tension measurements.
No, so that instrument is not able to do the pendant drop measurement, but what we have is there's a different dosing unit. So this dosing unit you can place inside the instrument where you can use other test liquids, and we can do the surface tension measurement from the SSL drop. So you can place the SSL drop on the surface, whatever the test liquid is, or your liquid is, and then you can get the information about the surface tension from the SSL drop. This will be, this will be one workaround. In most cases, if somebody is looking in doing the pendant drop and the testings, I would rather recommend the bunch top system, where we have exactly the same liquid needle, so you can still benefit from 2 seconds surface free energy measurements, and at the same time you can perform the pendant drop measurements whenever you have the need in doing so. Great.
And with that that different dosing system, you're essentially doing reversing the system of you have a known substrate and unknown liquids, whereas in surface free energy measurements you have unknown substrates with known liquids. So you're essentially flipping the situation there. So
exactly.
Good.